In this video, we're going to continue what we're doing with talking about vector-valued functions, and here we're going to actually cover a couple different topics. First topic we want to talk about is how to take a curve that we already know about and we don't have a function for, and find a function for it. Technically, there's not going to be a unique solution to this kind of question. There will always be multiple vector-valued functions that can work, assuming that we can find one in the first place. But being able to find a function that for our curve will be very useful if we want to do anything with it for various applications with calculus and all that kind of stuff. So that's what we're going to be trying to do. A function that does that for our curve is called a parameterization. So just what is a parameterization of the curve? And we can always say we can have multiple parameterizations of that curve. Unfortunately, there's not really a standard way of finding parameterizations, especially since there are such a broad number of parameterizations we could have. But let's look at a couple examples that come from the book and try to get a feel for the techniques that can be useful in there. So the very first one I'm going to do is problem 42. This is from section 13.1, so I guess it's page 895. And we're trying to find a vector function that represents the curve of intersection of the two surfaces. So here we have two surfaces. They intersect in a way, and the intersection is actually a curve. And I'm going to go ahead and show that to you as we go. But let me write down what they are. So first we have a cylinder given by the equation x squared plus y squared equals 4. And we also have another surface, but is not one of the standard surfaces that we looked at in the last set of videos. But we have a formula for it of z equals x times y. So let's plot these two. So first the cylinder. Pretty standard cylinder. This is the cylinder around the z-axis with a radius of 2, because we have the 4 there. And then our surface of z equals x times y. It's kind of a shape like that. Maybe let's give it a different color just so it looks a little bit different. Let's pick a. Oh, that's a little too bright. Does that work? I guess I'll stick with that. So we get a curve like, or a surface like that. Now, actually, technically, this is one of our standard surfaces, but it's not in the normal form that we actually looked at before. This is a quadratic surface because it has the linear term of z and the quadratic term of x times y. So keep in mind, if you have two variables multiplied together like that, it's actually degree 2. So this is actually a hyperbolic paraboloid, but we don't really need to know that to solve this problem. It's just GeoGebra recognized what it was. But notice here that we have a curve that is the intersection. Can it stop flashing? There we go. We have this curve that follows our surface and both of our surfaces. It has two high points on either side, and then it has two low points on the other sides. And we want to know what is the equation of such, or what is a possible set of equations that describes that curve. So, what can we do first? Well, the fact that we are working with a cylinder does actually help us out quite a bit, because that means we can think about what are parametric equations for this equation, for the curve that's given by this equation in the xy plane. So if you think about this, what is x squared plus y squared equals 4 in the xy plane is just a circle. It's a circle around the origin with radius 2. And if you recall from chapter 10, we know how to find parametric equations for such a thing. Basically, we use the fact that we know about the Pythagorean identity for sines and cosines, and we can turn that into a way of working with this. So remember, actually, let's start with cosine. Cosine squared theta plus sine squared theta equals 1. Or if we were to multiply things by 2, say 2 cosine theta squared and 2 sine theta squared, we can pull out the 2, and that gives us a 4 on the outside. So if we were to replace x with 2 cosine theta and y with 2 sine theta, those x and y would satisfy x squared plus y squared equals 4. So that's what we will actually do. And we can basically just take those as the first two component functions of parametric equations for this curve. Now, of course, that doesn't give us our z value, but we have a formula for z in terms of x and y. Basically, z is going to equal this x, so 2 cosine theta, times this y, so 2 sine theta. You can actually rearrange this a little bit. We have 4 times sine theta cosine theta. And if you remember some trig identities here, you'll remember that 2 times sine times cosine is the same thing as sine of 2 theta. So this is actually 2 times sine of 2 theta. Though technically we don't really need to do that last step. If you just looked at z equals 4 sine theta cosine theta, that'd be perfectly alright. Basically, these two formulas for x and y and this formula for z, those are equations, parametric equations for that curve. Let's actually go ahead and plot that curve, just to show that that's true. So we're going to take a curve. Don't forget my e. We said the first one was 2 cosine theta. Yeah, let's just go ahead and type in theta. We have 2 sine theta. And we have 2 sine of 2 theta, where our variable is theta. And I'm guessing because we're just working with sines and cosines, we only need to go from 0 to 2 pi. And that's not really sticking out very clearly. Let's actually make the line thickness a little bit bigger so we can kind of see it better. Maybe we'll do something like that. Hopefully that'll show up. Maybe not. Here. Let's make this a little less visible. Come on. Let me do this. Those are a little bit lighter, so you can kind of see now. That's not really showing up as well as I'd like it to. But kind of the point is that hopefully you can kind of see that the curve is following the intersection, even if the colors aren't really showing up very well. Maybe we'll just turn that back to black. Actually, that does show up better. I want to rotate it. There we go. So we have a curve that, given by those parametric equations, it follows that intersection exactly. It is exactly that intersection. And that's what we were looking for. And just notice that we use the fact that we could recognize the equation x squared plus y squared equaling something to make that work. It has a lot to do with being able to recognize various forms, is what makes actually finding parameterizations easier than otherwise. Let's look at another example. So the very next example in the book, 43. So very similar type of problem. We have two surfaces. First, they give us a cone, where z is equal to square root of x squared plus y squared. I would say here we might as well just go ahead and make this z squared equals x squared plus y squared. The only reason you might pick one over the other is that this formula here will only give you the part of the cone where z is positive. This would actually have two parts to it. Um, that's actually not going to be relevant for this particular problem, but it might be something you want to take into account. And the other one is just a plane. Plane given by z equals 1 plus y. And of course, let's go ahead and graph this first. So get rid of these. Stop that. There we go. So our first one, I'm just going to go ahead and graph it with the z squared, just so you don't have to worry about the square roots. So remember, our cone it has the two parts to it. Technically, we're only worrying about this top part. The bottom part is where z's are negative. And then we have the equation of the plane, z equals 1 plus y. So we have this plane that's coming through and hitting our cone. It's actually not hitting the bottom part at all. So that's why I'm saying it doesn't really matter here whether we have both parts of the cone. Now you can actually remember what this type of curve is. So I mean, when we're talking about conic sections, that's exactly what we're doing. We're taking a cone and we're intersecting that cone with a plane. And whatever that intersection is gives us one of our conic sections. It could be a circle, an ellipse, a parabola, or a hyperbola. And maybe if you remember right, you can kind of guess which one this is, but it's actually pretty easy to see if I just position it correctly that this is actually going to be the graph of a parabola. So whatever parametric equations I'm going to get are going to be the parametric equations of a parabola. Just not a parabola that's really oriented with respect to the end of the axes in a way that will originally make any sense to us. It just won't really feel like a parabola from the equations that we get. But it technically is. Now, how do we actually get those equations? That's the complicated part. And we're going to look at two different ways of doing that. So, idea one. First idea that we can have is, why don't we just call one of our variables our parameter? So, let's pick either x, y, or z and call it t. And we want to use another letter other than just x, y, or z, just so we can kind of avoid confusion, just so we know that we are dealing with parametric equations. But I'm going to start with the idea of our plane. So we have our z equals 1 plus y. How about we call y t? If we do that, so if y equals t, then z is 1 plus t. We get very easy, simple equations for y and z already. Unfortunately, x is going to be a little bit more complicated because the only way we're going to get at x is by using the equation z squared equals x squared plus y squared. And we're going to replace y and z with the equations that we have for y and z. So z is 1 plus t. We'll leave the x alone, but we're going to have to solve for it eventually. And then y is just t. So here we do have an equation for x and t. We just want to actually solve so that the x is going to be, we want to get the equation x equals an equation in terms of t. So, of course, we're going to move things around. We'll move the t squared over to the other side. Technically, we could leave this side as it is, but it will actually simplify nicely if we expand things out. So 1 plus t quantity squared is 1 plus 2t plus t squared. But then we have a minus t squared. So we can go ahead and actually cancel those two out. And just get 1 plus 2t. And then we can go ahead and take the square root. Unfortunately here, when we're taking the square root, we would have to consider plus and minuses. But when we're doing parametric equations, we want the formulas of x, y, and z to equal a function of t. So we can't just say plus or minus here, because that would no longer allow us to have a function. We'd actually have two different values of x for any given value of t. So for the moment, I'm going to just look at the plus sign. X equals positive square root of 1 plus 2t. Let's go ahead and, well, I should note here now that now we have x, y, and z parametric equations for a curve. Let's see what that curve actually looks like. So I have a curve. My x component is square root of 1 plus 2t, which isn't too bad. Our y component is actually just t, and our z component is 1 plus t. Of course, we have to put our variable of t, and we have to be careful here. We can't put in, well, actually, I guess we don't really have to be careful. GeoGebra will take care of things nicely for us. It'll just kind of ignore values of t that don't make any sense. So I'm just going to plug in minus 10 to 10. Of course, if we look at the square root of 1 plus 2t, not every value of t is going to work in there. You can figure out for yourself if you want to what the domain of that function is, but GeoGebra will just ignore t's that aren't in the domain. Actually, let's kind of thicken the line. Maybe that will work better. So here is our curve. Our curve is this part. So notice here, well, we did actually get part of the intersection, but we didn't get the entire intersection. We only got half of it. In fact, the reason why we got half of it is that we didn't put the minus sign. If we put the minus sign in there instead, we actually get the other half. So this is a parameterization of at least part of the curve, but we actually have to use two different curves in order to get the entire intersection. That could be a problem for you. Though this is a simple enough equation that maybe you're fine with that. Maybe you only care about half of it. Maybe you don't mind if we do it in two pieces. If that's okay with you, this would be perfectly fine. And it's not too difficult to get. But notice the technique that we used here is just calling one of our variables the parameter and just rolling with it and see what the other variables get. That's always a valid way of doing it, but it doesn't always give us the best equations. And sometimes you can run into some issues, like we just saw here. Another way of doing it, so idea 2. So we notice that we have x squared plus y squared equals z squared. This looks very similar to what we had before in problem 42. We had x squared plus y squared equals 4. And what did we do? Well, we used a trigonometric trick. We noticed that we could turn that into x equals something with cosine and y equals something with sine. But then we had to put multipliers in front to make this work, because if we just put cosine and sine, we'd get x squared plus y squared equals 1. We want to get z squared. So we're going to go ahead and multiply by z. Then if you square these and add them together, the sine squared and cosine squared part will go away, and you'll just be left with the z squared that you want. Now, of course, this is a little bit more complicated than what we had before. Before, we just had a 2. And 2 is a constant. You didn't have to really worry about it. Here, z is one of our variables. We will have to somehow get the z's out of this formula in order for this to be correct. So these are not our parametric equations yet for x and y. We're going to have to do a little bit more work than that. So where do we go from here? Well, remember we also have the equation z equals 1 plus y. Let's go ahead and replace the y in this equation with the formula that we have here. In other words, we're going to have z equals 1 plus our z times sine. So at the very least right now, we do have an equation that only involves z and theta. Sort of like how we had an equation that involved x and t in the previous idea. So we're going to solve this equation for z. So I'll move the z sine theta over to the other side and go ahead and factor out the z. So we have 1z, but we're subtracting the sine theta, and it's going to equal 1. And then we can go ahead and divide by 1 minus sine theta. Now, of course, that might be a little bit of an issue if theta is ever going to be equaling pi over 2 in this case. We don't want sine to equal 1 and still divide by it, though we will discuss exactly what that will mean for us in a moment. So we'll just roll with it for the moment and see what happens. And we can say right now that that's our parametric equation for z, because it's a formula for z in terms of a parameter theta. We still need to find out formulas for x and y. But now we know what the z is in terms of theta. So let's go ahead and replace the z's here with this formula for z. Give us more complicated formulas than we might have expected for x and y, but it will work. Essentially, we're going to take cosine of theta and we'll divide it by 1 minus sine. And then for y, we do the same thing, but now sine is on top. And these are parametric equations for a curve. Obviously, a curve that doesn't have domain all real numbers, because we cannot have sine theta equal 1. But we can still at least get an idea of what that looks like. In fact, we don't have to worry about that when we plug it into GeoGebra. It will take care of ignoring points that don't work. So have our curve. Here, of course, this is going to take a moment to type in. So here I have what I need for those three expressions. And then I'm just going to go ahead and pick 0 to 2 pi. Because all the functions in here, all the t's are actually going into a trig function. I just put in t just because it saves me some typing. So we have this. Again, let's make it a little thicker so it shows up better. There we go. Let's just be a little excessive about it. Now it'll definitely show up. But notice here, what we got was in fact the entire intersection, at least all the intersection that we can see. And we can kind of think about what is happening with this curve. As we put in values of t, what is happening to the points on the curve? I guess that it called it d, so let's plug in various points into d. Let's look at d of 0. Where is that point? Where did that plot that point? I'm not seeing it. Do I need to zoom in? Make sure I don't. Need to move that up so it doesn't cut it off. Why am I not seeing the points? Okay, so sorry about that. Because I made the curve a little really thick, it made the points not really stand out. They were there, just couldn't see them. So here, point A you can see from the tooltip if it decides to stay up there. I put in 0 as my parameter, and that is the point over here. So this is where t equals 0. If I plug in pi, I get this point over here. That's where t equals 0. This is where t equals pi. So I need to be able to select it. And then here, I went ahead and plotted this one while I was paused. Here I plug in 3 pi over 2. And that gives me this point over here. So somehow it went from t equals 0 over here to t equals pi to t equals 3 pi over 2. So what's going on here? Well, it's not very obvious exactly what's going on here if you're not really paying attention. Think about what happens if you plug in values of t. If you start at 0, you get this point over here, but you do not move this direction over to this point. In fact, as you plug in bigger and bigger values of t, you actually go off to infinity. So note here, I mentioned earlier that pi over 2 is kind of a problem spot. That's where 1 minus sine of t is going to be 0, and so it's not going to work very well. That's actually comes into play with this not actually being a closed curve, as you might expect from having sines and cosines. It actually starts here, blows up to infinity, and then kind of somehow comes back from infinity to hit down here at pi, then 3 pi over 2, and then returning back here at 2 pi. And then just doing the same thing over and over again. So you can kind of see from the equation here exactly what it's doing if you're paying close attention to it. But kind of the beauty of this one is that you do get the entire intersection, but of course the formula is kind of complicated. Having to have it over 1 minus sine of t is kind of an issue. You also are dealing with the fact that the where it does go off to infinity is at kind of an awkward pi over 2, stuff like that. But at least we do get the entire thing. So, kind of what's the most valuable thing to you in a parameterization? But having two different types of parameterizations could be useful for different types of applications. So, one is not necessarily better than the other one. But what we can kind of see there from that example, because we're looking at what happens as theta is getting closer to pi over 2, we're actually talking about a type of limit. So we can actually do limits with vector value functions in a very similar way as we worked with limits in Calc 1. Now, I'm not really pleased with the way the book actually structures its discussion about limits. It actually gives a definition that is really more of a result from the actual more formal definition. So I'm going to go ahead and present both of them. So they actually ask you in problem 54 to show from their definition the actual definition that is more commonly used by mathematicians. So notice here, this is an epsilon delta definition of limit. So dealing with these epsilon deltas, this is very similar to the definition of a limit that you might have seen, or you should have seen if you had a class that actually covered this. The definition of limit for just regular real valued functions. In fact, the format of this is very similar. So for real valued functions, the limit as x goes to a of f of x equals L. This means for every epsilon greater than 0, there is a number delta greater than 0 such that if you can essentially say the distance between x and a is less than delta but not necessarily 0, then the distance between f of x and L is less than epsilon. Or in other words, if we allow x to get close to a, then f of x gets close to L. Well, we're doing the same thing here, except in this case, when we instead of using absolute value to talk about the distance from between r of t and b, we're using vector magnitude. So r of t and b are both vectors. The difference between them is the vector between the two terminal points, and then the magnitude of that difference is actually what we want to say. That's how we want to say those two vectors are close to each other. So this is saying that as t gets close to a, then r of t gets close to b. And that's what it means for the limit of this vector valued function to be b as t goes to a. So we're just measuring closeness using magnitudes rather than absolute values. At least for the vectors over here, we're still using absolute values for the real numbers t and a. Of course, this formal definition is fairly complex, and it actually turns out that we don't really need to bother with it most of the time, but it is nice to know where things are coming from. So we're not really making up a brand new definition just out of nowhere. This is really just the old definition in a new context. So here's essentially a theorem that we can go ahead and prove from this definition. But this is what the book is actually putting forward as the definition of what limit of a vector value function is. Essentially, what this is saying is if you put your vector valued function into component functions, then the limit of that vector valued function is just simply the limits of the three components, or two components in the case of a two-dimensional vector value function, just put together into a single vector. Of course, this limit is only going to ever exist if all three of these limits exist. That you can actually prove that directly from the formal definition as well. If these limits don't exist, then this limit doesn't exist either. And if these do exist, well, this limit is made up from those limits, and so we're all good. But it means that to take limits for vector value functions, we don't really have to do anything special. We just take multiple limits of real valued functions, stuff that we already know how to do. And in case you're curious, the book actually asks you to prove this, or at least, yeah, it does ask you to prove it, but I'm not going to ask you to do that. But we have a result here that says that if we are working with vector valued functions and we look at our various operations, so we have our addition, scalar multiplication, dot product, and cross product, all three of those work with limits the way you might think they do. So the limit distributes over the sum, you can pull out constants, it distributes over dot products and cross products. So not too much to say there, except that it's very nice that things work the way we want them to. But let's go ahead and actually do a problem. So this is another problem from this section. It's actually problem 4. They want us to find a limit. Oddly enough. So the limit of our first component so our x component is t squared minus t over t minus 1. Our second component is the square root of t squared plus 8. Or not t squared, just t plus 8. And our third component is sine of pi t. Why did I do that? On a straight line. There we go. Over ln of t. And we're taking the limit as t goes to 1. Now we don't really have to do all this all at once. You could go ahead and write all this out and do all pieces at the same time, one after the other, but let's just go ahead and find the limits separately. So our first component is our first component function, I might say, is t squared minus t over t minus 1. I want to take the limit as t goes to 1. Of course, if I just try to plug in 1, things are going to break. We're going to get 0 over 0. But I can go ahead and just factor things. So I can factor the top as t times t minus 1. We can go ahead and then cancel the t minus 1's. So we're just taking the limit as t goes to 1 of t, which of course is 1. Just a normal limit from Calc 1. Our second component is actually even easier. We're taking the limit of t plus 8, square root of t plus 8. But because this is actually a continuous function at t equals 1, we can go ahead and plug in 1. So we get square root of 9 or just 3. We don't have to worry about pluses and minuses here. Now, of course, now we're dealing with the third component, which is the most complicated of them. In this case, we're dealing with sine over natural log. If we try to plug in 1, sine of pi is going to be 0. Natural logarithm of 1 is going to be 0. So we have a 0 over 0 situation. We can't really just plug it in. But what we can use is remember L'Hopital's rule. I'm not going to go through all that. If you don't remember what that is, you need to read up on it or maybe ask me questions, but I'm not going to cover it here. But the main thing here is that I can take the derivative of the top and bottom and then look at the limit of that quotient. So bottom is actually the easier one to do. We have ln of t, the derivative of that is 1 over t. The top, now I'm differentiating sine, and I'm going to get cosine. But I also have to worry about the fact that this is not just t inside here, this is pi of t. When I have to take the derivative of the inside, remember we're using the chain rule here, derivative of pi over pi times t is just pi. Pi is a constant. It says if we differentiate 2 times t, we get 2. So we put that derivative out in front. Now we have to think about what this limit is. And it looks a little bit more complicated than it is. We're dividing by 1 over t. That just means we bring a t up on top. So this is the limit of pi t times cosine of pi t. And if we plug 1 into here, well, here's just 1. Cosine of pi is actually negative 1. So we have pi times 1 times negative 1. Or in other words, we get a negative pi out. So our answer for this limit up here, well, our first component is 1, our second component is 3, and our third component is negative pi. That's our limit. And we don't really have to do anything more than that. So let's actually plot these points. So we've got a fairly complicated expression for this. We have the curve, where our first part is t squared minus t over t minus 1. Then we have square root of t plus 8. And then we have sine of pi times t over the natural logarithm of t. And, well, I can't put in t's that are less than 0, so we'll just go from 0 to 10, let's say. And let's actually, I need to change back to the normal view. There we go. You can always reset your view by clicking in a random spot and clicking standard view. Alright, here is our curve. It's actually not parallel to the red axis there. I think red is x, right? Yeah. It's not parallel to the x-axis. It is actually kind of going off in this direction a little bit. But we can kind of see here that we actually do have, it looks fairly continuous. It doesn't look like it has many breaks, but it does actually have a break where t equals 1. It has a hole there, just because we can't plug 1 in here and get something out. But if we were to plot the point that we just got, so remember we just got the point 1, 3, negative pi, that is a point on this curve. That's actually where t equals 1 would be if we could plug t equals 1 into the parametric curve. But as it stands, we'd probably just plug the hole that should be there, but just isn't really visible, by defining that to be what that curve should be when t equals 1. That's what we'd do. In other words, we're basically kind of talking about the ideas of continuity that we had back in Calc 1. So remember, a function is continuous. Remember, continuous means that we have three things. First of all, so let's say f of x is continuous at x equals a if f of a exists. The limit of our function at a exists as well. And these are the same thing. Technically, you could write this third equation of the limit of x goes to a of f of x equals f of a. Technically, by writing that equation, you're kind of implicitly stating that f of a and the limit both exist. But the important thing is that they are equal to each other when they do exist. So a function that does satisfy that at a is continuous at a if it satisfies that for all a's in a certain range. We say it's continuous on that range. And the whole idea here is that these conditions actually capture the idea of not having a break in the curve. Not having any holes, not having any places where it just suddenly jumps from one point to another, all that kind of stuff. Well, for vector value functions, we have exactly the same thing. Now that we have limits, we can actually say the same thing. You can say r of t at a particular value of t. We could write it out in three parts like we did there. I'm just going to go ahead and write out the limit as, not x, but a, t going to a this time, of r of t equals r of a. As long as the limits can be found by plugging in the number, then we say that the function, or the vector value function, is continuous at that value. So in this particular case, as we can kind of see from our picture here, this curve is actually continuous at every t other than t equals 1, where we had to actually find the limit, and we can't actually put in t's from 0 and below. Though we could actually find a limit from one side at 0 if we cared to. Now, of course, just looking at the picture does not actually prove that. If we took out this limit point at t equals 1, we actually can't tell from there that it does have a hole there because GeoGebra doesn't show that. So we'd have to say for any other t, we'd have to show that we can just go ahead and plug that in. But that's not too hard because the value for x doesn't really depend. The only place there's a problem there is when t equals 1, because that's the only place where t minus 1 is equal to 0. The square root is always fine as long as what we put inside there is 0 or bigger, and we're only putting in numbers where that number plus 8 is definitely a positive number, because t is always going to be a positive number anyways. And then finally, for our last one, the natural logarithm, as long as we put in positive numbers, that's only equal to 0 when t equals 1. So 1 is the only problem spot. But all the same ideas that we had about continuity back in Calc 1 extend just as they did, as we expect them to, to vector valued functions. Alright, so the only other thing that we can do here is mention that after limits and continuity, the next step up would be going to derivatives. So that is what we are going to do in the next section. So the next video is coming up in a day or two, will be about derivatives, and in fact we'll actually talk about some integrals of these vector valued functions. So finally getting into some calculus in this class. And I'll see you guys in that next video on actual calculus. So see you then.